Okay, so I think we can start now. It's 7 past 8 already. So hi guys, good night. I'm Andrian Huang. Today I'm going to be your presenter for this workshop. So before we get into the material, uh, perhaps I'll introduce you guys to MLDA at Triple E. So MLDA at Triple E is a student-run lab to provide platform to empower Triple E and IM students to learn and deploy machine learning and data analytics skills in both academia and industry settings. So how do we do that? We do so through various events, projects, and activities. And we also impact knowledge and skills for machine learning through 4 different pillars. So we have ML projects, industry projects, we have career events, workshops, and competitions. So that's briefly what MLDA Triple E does here and our missions. Okay, just to make sure, can you guys hear me? All right, sure. Okay, so without further ado, let's get into the material. So today, of course, we're going to talk about neural networks. It's a broad category. There are a lot of types of it, of course. Uh, which one do you think is suitable for image classification problem? Some of you might know, right? So it's called CNN or convolutional neural network. So today we're not going to dive deep into how CNN works, but we're just going to touch a bit on this because this is the network that we're going to use later on. And then there are some concepts that we might need to know to discuss about this. All right. So imagine you have a picture, right? A picture is actually a really big input data because it's 2-dimensional, sometimes even 3-dimensional because you have color. So if you do it the conventional way, for example, using a fully connected network, uh, you're going to have to connect each pixel and each color of the pixel into an individual network. So if you do that, you're going to end up with a lot of networks and a lot of parameters. So that's going to be computationally expensive, right? But convolutional neural network can alleviate this by using what's called the convolution. So it's an operation I'll show you guys later. So this is this picture shows how CNN works in general. As you can see here, you have the input image, and then it performs convolution, which I'll show you in the next slide. And after that, we'll use a fully connected network to classify the output of the image. So that's about it. If you guys want to know more, you can visit the link below. Don't worry, I'll share the slide later. Maybe some of you guys also attended the CNN workshop by MLDA Triple E a few days ago. So in those workshops, we dive deep into how CNN works. Okay, anyway. Okay, so this is the convolution operation. All right, so on the right here, I have a simple animation. So the green matrix here is your input image, right? For simplicity, we have zeros and ones only. And then the yellow one here is called the kernel. So essentially, the convolution operation is just the multiplication between the kernel and your input image. And then you slide the kernel so that you cover the whole image, yeah, as you can see here. So then the output will be the convolve feature on the right here. And there's actually a special name to this. This is actually called the feature factor or the feature map. Okay, so that's convolution operation in a nutshell. As I said, we're not going to dive deep into it, but then that's the basic of it. So the output is a feature map, right? So why do we want to do this? Well, the feature map contains the features of the input image, for example, edges, lines. And then if we do this operation multiple times back to back, right, we can actually extract high-level features of the image, and that's our goal. So for example, if you want to detect maybe a face, then you can do multiple convolutions using multiple kernels, of course. And then in the first few layers, maybe the feature is simple, such as lines or edges. But then at the later layers, you can find features such as maybe nose or eyes or something like that. Okay, and then there are a lot of CNN architectures as well. There are VGGNet, AlexNet, ResNet. There's a lot, and then research is still going on. Okay, so this is an example of feature map. So on the left here, we have the input image. And then on the right, you can see various feature maps there. Some of those you can see that they detect line. Some of those maybe detect points. Well, the feature map doesn't necessarily mean that you'll detect lines or edges or something like that. It's actually a learnable parameter, so it might not mean anything if you see it directly. But if you run the model, then you may you may notice that it actually works. Okay, another thing that you may notice from this is that on the rightmost image, you can see that the resolution of the image is actually reduced. So this is another powerful feature of CNN. It reduces the number of parameters that you have to tune in order for you to make the model can predict. So compared to the fully connected network, CNN is much more efficient in the parameters because you have less of it. Okay, so we have the CNN. CNN is great for image classification. It actually scores amazing. It's actually being used a lot today as state-of-the-art model for image classification. So we already have that. Now we want to do object detection, right? So you might think that, okay, we have CNN now, and we know that it's great. So we can just apply it to object detection, right? Because they're just the same. Well, actually, it's not as easy as that, as you can see later. All right, so what's the difference between object detection and image classification? So on the left here, we have our usual classification problem. So we have an input image, which is a cat, and then the model should be able to classify that it's a cat. So that's just image classification, which we can solve using the CNN. And then one level above that is classification and localization. So instead of the model just telling you that it's a cat, it actually also has to tell you that the location of the cat itself. So for example, here it's drawn by the red rectangle. Yeah, and that's one level above classification. And then we're still playing with single objects here. And then if you go one level, higher, then we'll get into object detection, which is our goal today. So as you can see here, we have a lot of objects in one picture. So if you apply CNN to this, you'll not be able to get meaningful result because you have multiple objects, while the usual classification problem can only detect like one object for a picture or so. So in this object detection problem, we might have multiple objects, and then the model should be able to detect where the objects are and detect individually what the objects in those bounding boxes are. So as you can see now, it's not a really simple problem. You cannot just solve this using the CNN. You need something else. And then if you're curious, you can actually go even one level higher, which is called instance segmentation, or sometimes object segmentation. So instead of just drawing the bounding box there, you draw the outline of the object itself, which is, well, even harder, you know. Okay, so we have the CNN, right? We have a tool which allows us to classify objects. So the question is now, how do we leverage on CNN to perform object detection? Okay, so some of you might already know perhaps the naive solution. So imagine you have a picture, let's say a cup, right? And then we want to detect the presence of object in this image. So what we can do is to break this image into smaller pieces and then check the pieces one by one if there are objects in it. So for example, here I can have this segment, and then we'll feed this segment into the CNN, and then to try to find out whether there are objects in this segment. In this case, there isn't really any meaningful object, so maybe the output is just a random guess. And then what we can do is to pick another region or select the region or perhaps pick another size. So let's say this one. And then maybe the model will say, well, that's a cup, but not really confident about it. And then we can slide it more. It comes into a clear picture. Then when we reach a certain region, we might hit the perfect spot, and then the CNN will tell that it's a cup and it's very confident about it. Congrats, you just found an object. So this is actually doable in real life, but as you might know, it's actually a very slow process, right? Because imagine how much regions you have to create out of this. because you're gonna have multiple objects, and then the objects will be of different sizes. So you're going to have to guess a lot of regions, maybe even like hundreds of thousands of them. So even though this is doable, this is not how we do it in real life. So now the question is, can we actually propose regions more efficiently? Well, there are algorithms in the real world for doing that. And the one that we're going to look today is called the selective search. So let's say with the picture here, we have a cup, we have cups, we have some glasses, and then the first step of this algorithm is to actually group based on the intensity of the pixels. So this means that you're trying to group neighboring pixels based on their intensity. If they're similar, then they're going to be in the same segment. So the output can be something like on the output image on the right here. Okay, so all right, so we're one step closer right now. Okay, but then the problem is, can we directly use this as the proposed regions? Well, the answer is not really, because as you can see here, it's kind of over segmented, right? For example, the cup here, even though it's a single object, it has multiple segments in it. So what we have to do next is to actually kind of join these segments to form less region proposals. And we do that by grouping adjacent segments by similarity. So for example, here on the bottom image, you can see that it's over segmented. And then what we can do is to group adjacent regions, which are similar in perhaps size or shape or colors. Then when when the number of segments is just right, we can use that as the region proposal, which is the resulting image on the right here. Okay, so that's selective search. Okay, this is the simplified version, but in the real life, it's kind of similar to this one. Okay, with that said, we now actually arrive at RCNN. So RCNN is region-based CNN. The R stands for region-based. So this picture here tells us how RCNN more or less works. So we have the input image here, and then before we feed into the CNN, we actually create region proposal. So let's look at that. So since we discussed about selective search, then obviously the algorithm that RCNN uses is selective search. So for RCNN particularly, we're trying to find about 2,000 region proposals using this selective search algorithm. So after we find these region proposals, we then feed it into the CNN for classification. But we have a small problem, because if you remember, CNN actually has a fixed input size, right? But then our region can be of different sizes and shapes. So before we actually feed into the CNN, we have to actually warp the region of interest into the correct size so that the CNN can process and extract the features. Okay, after that, we can directly feed into the CNN, which will extract the features of the individual region proposal. One thing to note here is that actually for this algorithm, right, for RCNN, since one image produces like 2,000 region proposal, then for a single image, you're going to run the convolution and feature extraction like 2,000 times. Yeah, so that's just how RCNN works. One image produces 2,000 region proposals, and for each region proposal, you feed that into the CNN so that it can extract the features. All right, so once you extract the features, you're going to feed this feature factor into a classifier. So a classifier is just a model that lets you classify, and then in our case, it's a binary classifier, meaning the output is a yes or a no. In our case, we're using a model called support vector machine, or SVM. Maybe some of you might know. So for this particular case, we can see that the feature factor is fed into the SVM. And then actually we have a lot of SVM, one SVM for each class. So for example, we have aeroplane class, person class, and TV monitor class. This means that there's an SVM just for classifying whether the image is an aeroplane or not. And then maybe another another SVM to classify whether that's a person or not, and so on and so on. So we're going to have a lot of SVM. And then for each feature factor that we get from each region proposal, we're going to feed this into the multiple SVMs. And then the one with the highest score will be the classification output from the model. Okay, so that's it. That's kind of how RCNN works. But then there's actually one more optional step, which is called the bounding box regression. So what this does is that when the selective search algorithm actually proposes region like this, it might not be really accurate, right? For example, here it doesn't really enclose the cup. So what the model can do is that you can also feed the feature factor to the bounding box regressor, which will kind of adjust the bounding box so that it fits the image. So we're not going to dive deep into how this works, but then it's actually an optional step, but it actually can increase the accuracy of the bounding box. All right, so that's RCNN in a nutshell, right? So first of all, you have selective search to generate the region proposals so that you kind of know which region of the images, which part of the images that might contain an object. And then after that, you have the CNN, which will extract the features of the object inside the region proposals. In this case, 2,000 of them for each image. And then after that, we're going to have the feature factors as the output of the CNN, and we're going to feed that into the classifier to classify what object it is and whether there's an object in the region or not, and also to the bounding box regression, so that we can kind of adjust the bounding box so that it kind of fits the object more perfectly. Okay, one thing to note here, for selective search, although it kind of try to find objects, meaningful objects in the region proposal, it might not always find so, right? Sometimes it can propose a region that has no object at all, and that's actually fine because the CNN can filter whether there are objects or not in the region. What's important from selective search algorithm is that we have a high recall. So a high recall means that if you have an object in the region, then the model will very likely to say that to pick a region that contains an object. So we can pick another case, for example, cancer detection model. If your model has a high recall, then it's very likely that if a person has cancer, then the model will tell you that the person really has cancer. So in this case, it's actually not really important if you have false positives. What's important is that you catch all the positive cases so that if the person really has cancer, then he or she will get treated correctly. So that's our criteria for selective search, high recall. We want to make sure that we select regions that contain objects. Even though subregions might not contain objects, that's fine because the CNN can take care of that. All right, so as you can see here, it involves a pipeline of several different operations, right? Firstly, we have the selective search, then we have the CNN, we also have the classifier and the bounding box regressor. So that's a lot of operation actually. And then for each image, you'll do that 2,000 times. So you might already imagine that RCNN will be very slow, right? And actually that's the case. RCNN is a very slow algorithm. And then it has several disadvantages as well. So the first one is obviously is computational expensive because a single input image will produce like 2,000 region proposals. And then for each region proposal, you're going to feed it into the CNN. So just for one image, right, you're going to have to extract 2,000 feature factors. And then for all those feature factors, you're going to have to feed it into the SVM. That's a lot of computation. And then as a consequence, it takes a really long time to train and run. It can take like tens of hours to train this. Due to this, we're actually not going to train our model later on. And then we're actually going to use a modified version of RCNN. We'll get into that later. So RCNN is very slow and everybody knows about it. So forget about putting RCNN into driverless car because it's not going to work, right? Okay, and then the next disadvantage that RCNN has is that it uses the selective search algorithm. It's actually a fixed algorithm, so there's no learning happening here. So there's a chance that this algorithm doesn't really perform well in selecting region proposals. which is actually crucial for this object detection algorithm. And then selective search itself is actually quite slow, as we see later. And then lastly, RCNN involves like 3 separate models that needs to learn and run separately, as you saw before. It has the CNN, it has the SVM, and then it has the bounding box regression. So this is the main reason that RCNN is not really used today. But not to worry, because RCNN actually laid the foundation to later modified models of RCNN, which is actually state of the art today. So the question is, can we go faster? Well, of course. So the very same author that created RCNN actually know these issues. And then in the next year, he actually addressed that. So he called that fast RCNN. So instead of feeding 2000 region proposals per image into the CNN, the input image itself is actually passed through the CNN to produce the feature factor before we pick the region proposal. So instead of 2000 feature factors per image, you now only have 1 per image, which is a huge computational speed up. And then the region proposal will be picked from that feature factor. One thing to note here is that we're still using the selective search algorithm here. But this improvement alone is really noticeable. All right, so we're not going to really touch deep into the fast RCNN because we're not actually use that today. And then the question is, can we actually go even faster than that? Well, turns out yes. And then the model for that is called faster RCNN. So the reason why we talk a bit about fast RCNN is that because faster RCNN actually uses fast RCNN, and then this is the model that we're going to use today. So recall that in the vanilla RCNN, right, we have the selective search, and then we have the CNN, classifier, and the bounding box regression. So as it turns out, the selective search process is actually a very slow process, even though in fast RCNN, we have improved the model by not doing 2000 region proposals and feature extraction from those. It turns out that the selective search algorithm now is the bottleneck of the algorithm. So how do we fix this? Well, an intuitive approach is to actually not use selective search at all. So that's what faster RCNN does. So what do we do then? Well, so instead of using selective search, we now use a region proposal network. So it's actually a separate learnable network. So it's not a fixed algorithm anymore. It's actually a learnable network with parameters itself. And then to perform classification, we use fast RCNN. Okay, so this is why we discussed about fast RCNN a while back. So if you see the picture here, we have the region proposal network, and then we also have the RCNN. But it looks like we have 2 models, right? But actually, in reality, the 2 models are unified into a single model. So both of these 2 models will share the same convolutional feature layers, or share the same feature factor. So they'll be very efficient. And as the result, inference with faster RCNN is quite fast. And then some people actually do it for real-time applications. And then accuracy is actually also fine. And then, so this is why faster RCNN is the go-to RCNN algorithm if you want to do object detection right now. All right, so without further ado, we can go into the coding session. So you can access this link here, tinyurl.com/RCNN workshop. Okay, let me change my screen. All right, at this point, if you guys have any problems downloading the code, you can let me know. All right. There are a few chats there. Let me see. Okay, sure, sure. All right. Okay, so once you access this link, you'll see a folder. It's called RCNN Workshop. So what you can do is to download that folder and then put it in your own drive. So for example here, I put it inside a folder called Colab Notebooks. Yeah, right here. And then just put it there. Okay, the slide is also inside the same folder, so that's for your own reference. Okay, shall we start? All right, so now you should be able to open the Colab notebook. So Google Colab is actually a platform for you to run Jupyter notebooks without actually you installing the Jupyter notebook or Python modules itself. So it's actually a convenient way to run codes because you don't have to set up the environment yourself. And then you actually have free access to GPU or TPU accelerator, although the access is limited with free Google Colab. But still, it's actually a very nice tool to have. All right. So we'll start by mounting your Google Drive. So the purpose of mounting your Google Drive is that so our code can access files inside the Google Drive later. So simply run this, and then okay. So I've already mounted this. When you run this, you should be prompted to insert code. So you just follow the link, and you should be able to mount the drive. Okay. The link for the code is this one. Can you access it? Actually, it's inside this. It's inside this link. All right. Let me know if you have problems. Oh, okay. Let me check. Is it leading to Zoom for you? Because it seems to work fine for me though. All right. Maybe I can try. I can try to share another link with you. So see if you can download. All right. This one is lengthy. In case you cannot use the tiny URL, maybe you can try this one. When you open the longer link, right, you download the Colab notebook first, and then you put it inside your own drive. Okay, does anyone else have problems? All right. So, okay, back to our code. So the first step is to actually mount your Google Drive. In our case here, I've already mounted. And then if you click this icon on the left, you can actually expand the file system of Colab. So here I've run several things. So in your case, you will only have drive and sample data. Okay, so I guess we can proceed. And then the next one is to actually clone TensorFlow models. So for this object detection demo, right, we're going to use TensorFlow object detection API because this API actually provides us with pre-trained models. So that means we don't have to train the model from scratch because that's going to take a lot of time, especially using Google Colab. So it's really convenient because you don't have to train the model at all. You just need to download it and then restore the checkpoints, and you should be able to directly run inference, which is what we're going to do today. Okay, anyway, the model are trained using the COCO 2017 dataset. So COCO is a common object in context. It's actually a database by Microsoft, I think. So it really is a large object detection database. It contains 300,000 images. So it's actually a common database for you to train object detection models on. So in our case, the pre-trained models that we're going to obtain today uses this to train. Okay, without further ado, we can run this. Okay, I've run this before. In your case, it should download the TensorFlow models repository, and you should be able to see it here on the left. In case you don't, you can try to press the refresh button here, and you should see this models. Okay, anybody has problems so far? All right, I think we can continue. So after we clone the repository, next we're going to install the TensorFlow object detection API. So you can do that by running this cell. And then this might take a while. It's fine. A note, right? If you encounter dependency errors, then you need to run the cell twice and it should resolve the problem. So for my case, I've already run that. So requirement already satisfied. Everything seems fine. Most likely you need to run this cell twice to resolve the dependency problems. That's fine actually. Okay, maybe I'll wait for a minute because this can take a while. Okay, at this point, let me know if you have problems. Okay, let me see. Have you run the cell before this one? Okay, sure. Let's try that. Okay, let me know if you have problems. So I believe for the others is going fine so far. Okay, in the meantime, right, once you have done this, now you should be able to test the installation. So before we already installed this one, right? Now we need to test it. So for this one, the output is going to be quite long. You should see something like this. But the most important one here is the bottom one, ran 20 test, skip one. I got this and everything ran fine. So you should be able to run this and then wait for the output. Okay, anyway, right, if you run this notebook without GPU, which is the default runtime type, then you get this error somewhere in the line. Okay, let me search. Yeah, you can get this error message saying no CUDA capable device is detected. This is actually fine. We don't really have to use GPU right now. And then you can actually resolve this error by changing the runtime type. So you can actually go to runtime, then change runtime type, and change this to GPU. But in that case, it doesn't really result in significant speed up because I tried that, but it resolves this error. Okay, it's working now. Okay, sure. All right, so that's it for the setup. The next one is to actually prepare the model itself. So first thing first, we're going to import the libraries that we need, including TensorFlow itself. And then we'll also define the functions that we're going to use later on. For example, this function here, the use of this function is to convert an image file into a NumPy array. So NumPy is just a high performance numerical library for Python. And then this one is to actually get key points later on in the model. So we just go ahead and run that one. Let me know if you have errors, but I don't think you should have error. So in my case here, I'm running with TensorFlow version 2.3. It should be similar for you. Okay, then after that, you can go ahead and choose the model. So here we have 5 different models. All of them are faster RCNN. It's just a different variation of the CNN architecture. So for this model, right, we're going to use ResNet, which is a type of CNN. It's actually a state-of-the-art CNN architecture to date. So the 50, 101, and 152, they are actually the depth of the ResNet layer. So the default is this one. We're going to go with the deepest one. And then just run that. And then once you have chosen the model, you can go ahead and download the checkpoint for the model. So if you see the code here, it's just a simple if else because every model has its own download link. And then you can actually find the download link here. Okay, it's done. So once you're done, right, you should be able to see this. So what it does is that it downloads the checkpoint here, as you can see. Okay, up to this point, let me know if you have problems. So far, it should be fine. Okay, so what this does is that it downloads right, and then it extracts the checkpoint, and then it moves into this folder. So that's what we're going to need to do for later. Anyway, once you have done this, you can actually restore the checkpoint. So the checkpoint is actually a record of the exact parameters of the model, right? So if you have trained a model and then you have to kind of save the model, what you do is to save a checkpoint of that model. So you can share this checkpoint with others, or you can keep it for yourself. So later on, you can restore this checkpoint, or others can do so. So you don't have to train the model from scratch. It already saves the parameters for you. And this is actually what we're going to do today. So the TensorFlow team has actually trained the model for us on the Coco dataset. So what we have to do is to just restore this checkpoint, and we already have the model that's already pre-trained and ready to be tested. So to do that, we just run this. Besides restoring the checkpoint, right, we also define this function. So in Python, you can actually write a function that returns another function. So this is what this function does. So this function will return us a function that lets us convert a raw image in NumPy array format into the predicted output. Okay, up to this point, you should have no problems. Let me know if you have some. And then the final one before we can run the test is to actually load the label map data. So the label map data is just a Python dictionary. We use that to translate the index number predicted by the model into the actual name or the actual label of the object. So for example, here we use the Coco data set, and then we have 80 categories like airplanes and Apple backpack and things like that. But in the model itself, it's not going to be represented in labels. It's going to be represented as index numbers. So we need this label map, which is a Python dictionary, to convert that back into the correct label. And then inside the TensorFlow model repository, we actually have that already built in for the Coco data set. So we can just run it. And then as you can see here in the output, we have a lot. We have 80 categories here, which is what we should expect from the Coco dataset. And then these are the objects that the model currently can detect because the model is trained on these. Yeah, so we have quite a lot of objects here. Okay, so that's it for the setup. So right now we can actually already run the model and see whether it can inference, it can do inference and then detect objects in the picture. All right, so I believe this is what we're waiting for. Okay, so the TensorFlow models repository actually has built-in image. For our case, we have two of them, image1.jpg and image2.jpg. We can use them to test the model. So for this part, you might need to be patient because it might take a while. Yeah, maybe a minute. It's not really long though. So if you wish to change the image, you can do so from here. You can change it to image1. And then, as you can see here, once we specify the input image, we tell the full path here, and then we'll convert that into a NumPy array using the function that we have defined before. And then we can run the inference. So the inference is this whole chunk, but we can encapsulate that into a simple function here, predict and draw, for example. So all this is using the TensorFlow object detection API. So it might look daunting at first, but this is actually, there are actually a lot of tutorials on this. And then there are a lot of example codes online. So actually for this notebook, it's adapted from the official tutorial from TensorFlow. But then if you run that tutorial directly, right, it will not run because you have to do some modifications, which I did. So anyway, after we do the inference, we can actually plot the image and see the result. And lastly, we can use the function that we define, and then we input our image and then the minimum threshold. So what is this minimum threshold, right? It's actually the minimum score, the minimum confidence for the object detected to be shown in the image. So you can run this. In my case, I've already run this, and this is the output. Yeah, so as you can see here, we have a lot of objects. We have a lot of person here. And then if you can see, the confidence is actually not bad, 98, 100, 95. And then we also have several kites. Well, to be fair, this is actually a simple and easy image. That's why the model performs quite well. You can actually change this into the first image, which I think is kind of harder for the model. Okay, I can run that also. Okay, up to this point, you can let me know if you have problems. But by right, you shouldn't have any. Okay, this might take a while. So for those of you who are curious, right, you can actually try to change the runtime to GPU here, which I told you guys before. But actually, I tried that. I didn't find any significant performance boost. Maybe because it's not really utilizing the GPU, even though we changed the runtime. Okay, I'll wait for a while, maybe 1 minute. Let me know if you guys have problems. All right, there you go. So this is the other image example from TensorFlow. So as you can see here, sometimes it mispredicts, right? So it's a dog picture here, but then the model says it's a horse. Well, to be fair, it looks kind of similar. We know it's a dog, but for a model, it's not really clear. And then if you can see the score there, it says 63%. So the model itself is actually not really sure that that's a horse. But then since we set the minimum threshold to 0.4, this prediction gets displayed anyway. Okay. Also, we can actually see some correct predictions. For example, the green box here, it says person, because if you see carefully, we actually have a person standing here. It's just the feet, so it's kind of tricky. But then the model did a pretty good job at detecting that as well. All right. So far we run the model on test on example images, right? Can we actually do more tests? Yes, we can. So remember that before we run the code, we actually mounted our Google Drive. So the purpose of that is to actually upload our own images so that we can test the model on our own image. So in this section here, you can actually upload any image you want to your Google Drive. So a way to do that here is, okay, let me hide this. All right. So you can find an image, preferably the size is not too big, because if the image is so big, right, later on, this caption here will not be visible because it will appear small. So the test image here has the size of, well, just below maybe 1,100 by 700. So you might want to find a picture with similar size. Or maybe you can just Google some pictures and then screenshot it. And then next, you'll want to upload it into Google Drive. So you have downloaded this folder, right? And then you can see this folder, custom test image. So you can put whatever image you want here, and then you can rename it so it's easily identifiable. All right, you can download any image you want, as long as the objects are listed here, which are inside the Coco dataset. Okay, some remark about this, right? Maybe you downloaded this RCNN workshop folder in a different directory. Then in that case, later on, you're going to have to change this line. So if you downloaded this folder and put it inside my drive, Colab notebooks, then you should be fine. But if you put it in a different directory, then later on, we're going to change this line. But it's actually not a hard process. So what this is actually the full path towards the folder where the images are. So for example, here, since I put it inside my drive, Colab Notebooks, RCNN Workshop, then that's what the custom image directory will be. So as you can see here, and then you can actually navigate on the left panel here. So let's try content, drive, my drive, Colab Notebooks, RCNN Workshop. Yeah, as you can see, you should be able to find the images here. Or you can also try the alternative here, which is upload to session storage. You can click this button to try to upload directly to this. But alternatively, you can also you can also upload to Drive. Okay, inside the folder here, I've already put 3 images for you. You can feel free to add more images. You can also take a selfie of yourself if you want to. Well, why not? All right, so I believe we can proceed now. Okay, so first of all, we choose one image that we want to test on. For example, I choose image 3, which is this one. And then again, we can specify the minimum threshold. I'll leave it as 0.4. And then Using this, we concatenate this and this to form the full path of the image. And then we feed it into this function, which we defined previously, to convert the JPEG into NumPy array. And once we're done, we can just call this function that we made previously to run the object detection. So I've run that before, and this is my result. Okay, on your side, it might take several seconds to run. So, okay, let's see some detection here. So suitcase, that's correct. Car, person, handbag. Okay, one interesting thing happening here is that baseball bat. Well, there's actually not a baseball hat here. So what happens here is that if you see, to be fair, is kind of similar to a baseball bat. Uh, I mean, this is a model after all, right? It's not a human. So, and then if you see in the COCO dataset category list here on part 2.4, you can actually find baseball bat somewhere. Yeah, there you go. Yeah, so when the model sees something that it believes is an object from the AT category, then it'll just show it. Yeah, after all, it's a model. You can actually try multiple images and see how it works. Okay, so this is basically it. We basically download a pre-trained model from TensorFlow repository because it's kind of impossible to train from scratch because they'll take a very long time. But then, as you can see, using several lines of code, it's actually not really hard. You can already do object detection. One thing that I miss from running on my own laptop instead of Google Colab, right, is that you cannot do using webcam because unfortunately, OpenCV doesn't really work with Colab. Some functions does work, but then you cannot really access the webcam, or maybe you can, but then it's not really trivial to do. So if you run this code on your own laptop locally, you might be able to do so. Feeding input image from your webcam and then feeding it into the network. That's totally possible. And then you can actually do that. There's a lot of tutorial doing so. But since today we run on Colab, right, we're not going to do that, unfortunately, because it's not really easy to do. Okay, does anyone have problems so far? I believe not. So feel free to keep running this. But actually, there are a couple more things to try out. So remember that you can choose between models, right? Over here. Yeah, this one. Section 2.2, model selection. So here I included 5 models. Remember that we ran this one. You can actually try to run other ones. So this is the deepest one, right, with 152 layers deep. So you can try a shallower one, for example, the ResNet 50. In general, right, the deeper you go, the better the accuracy will be. But that's not always the case. But for this one, actually, it kind of is. So if you navigate to this website here that I put the link. Okay, so this is the official page for TensorFlow 2 detection model. So as you can see here, there are a lot of models, CenterNet, SSD, single shot detection, and then faster RCNN, right? So if you click this, then you'll download the checkpoints. So basically, this is what this cell does, downloading the checkpoint according to what model you specify. So feel free to change the model and see the result. And also other thing you might try is to actually change the minimum threshold, which is this one. So you can try lowering this value, then you should expect to see more boxes. Okay, the reason it takes some time in Colab, right, is that perhaps it's not using hardware acceleration. And then since you're not running locally, then you should expect this kind of performance. And then Colab itself is a free service, so that Google has to kind of distribute the resources evenly. But actually, you can subscribe to Colab Pro, which is a paid version of Colab. Uh, for that, you're going to get a better support. Okay, so as you can see here, I lowered the minimum threshold to 0.2, which means that any prediction with the confidence above 20% will get shown. So as you can see here, we get more objects now. Yeah, person here 30%. There's not really a person, so it's not correct. And then handbag. This one's not really handbag. As you can see here, the the score is not really high, right? It's only 30%. But then since it's above 20%, which we set here, then it gets shown anyway. So this is like one of the parameters they can try tweaking to get the best result that you want. Okay, so that's it for today's collab. Maybe you might be thinking, right? How about if I want to train on my own data set? How about if I want to classify, for example, different cars, different brands, or whatever object you might have? So in that case, you can do what's called transfer learning. So transfer learning is basically using a pre-trained model like this one, but then instead of using it directly, you also train the model additionally on your own data set. So the benefit of transfer learning is that instead of training from scratch, which will take hours, you can actually use a pre-trained model which already has the weights kind of correct, and then if you do transfer learning instead of training from scratch, then the training time will be shorter. But transfer learning is not going to be covered here. Actually, there's a MLDA workshop on transfer learning, but I think it's already like a few weeks back. But not to worry, there's actually a lot of tutorials online to do transfer learning on this pre-trained data set. It's just that it's not as easy to do as this one. And actually, TensorFlow repository also has some built-in image. So if you navigate to models, research, object detection, test image. Yeah. So as you can see here, these are the two images that we test on, right? Image one, image two. And then we also have this ducky folder. So this is a collection of some duck images. So this is the built-in examples that they ship you with, that they ship this model with. So you can actually train the model on this. So if you want to do transfer learning, you can actually use this built-in train and test images. But that's kind of the scope of today's workshop. So for the coding session, this is kind of it. So let me know if you guys have any problems. In the meantime, we're going to go back to the slide later. There are a couple of more slides there. Okay, so you can let me know if you have problems. Meanwhile, I'll go back to the slide. All right. Anyway, feel free to save the code and use it for your own purpose. It's actually available online also, but I did some modification because it will not run directly. Okay, so you might be thinking, right? Can we go further than this? Well, actually, you can. If you remember previously, there's actually one level even higher than object detection, which is called object segmentation or instance segmentation. So instead of just drawing the bounding box, you actually trace the object. So you can see on the left image here. So that's what object segmentation model does. And then uh, to do that, there's a variant of RCNN called mask RCNN, which is actually an improvement of faster RCNN that can do this kind of thing. So we're not going to go to that for now, but then here's the link if you want to read more about it. And then since I'm going to give you the slide, you can actually access the link. Okay, so this is object segmentation, right? Okay, so another one is that can we actually go even faster than this? Well, you can do that, but then you have to venture beyond RCNN. And the model that you're looking for this job is actually called YOLO, or you only look once. So it's not RCNN anymore, but YOLO is actually another state-of-the-art model. It's also widely used and well-known. And if you're actually curious to find out about this, right, you can either follow this link, or you can actually sign up for tomorrow's workshop by mlda triple also, which will be discussing about YOLO. So we're going to do the similar thing, which is object detection, and then we're also going to use the pre-trained model. But then instead of using RCNN, we're going to use YOLO. So YOLO, as the name implies, only looks at the image once, right? So as you can imagine, it's going to be a lot faster than RCNN, even faster than faster RCNN. But that comes with a downside, right? If you compare with faster RCNN, YOLO is faster, but then it struggles more if you're trying to detect smaller objects because of the way it works. And then in terms of accuracy, although it's actually quite good, sometimes it does not come in par with faster RCNN. So that's the two differences between faster RCNN and YOLO. If you want to know more, you can read this or join tomorrow's workshop. Okay, so with that, that's the end of the workshop. Thank you very much for joining me today.